This is lesson 1.2 on functions. By the end of this video, you should be able to describe a subset of the real number system, determine whether a relation is a function, evaluate functions, and state the domain of a function. We're also, at the end of this video, going to get a look at a new type of function that you've never seen before, which is called a piecewise function. You're also going to be able to describe sets of numbers using something called set builder notation. Let's jump right to it. So the first topic we're going to talk about is the set builder notation. So the real number system is used to describe quantities such as money or distance, and the set of all real numbers includes the following subset of numbers. So I want you to get this table into your notes. Let me get the pen going. There we go. So this table should go in your notes. So this Venn diagram is meant to illustrate the real number system. For all intents and purposes, the real number system is the largest number system that you're going to work with for most of the year. Towards the end of the year, we'll introduce a much bigger number set that actually contains the real number system called the complex number system. But for right now, the largest set or the universal set is the real number system. And then within that number set, we have smaller and smaller and successively smaller number sets. So let's start all the way at the inside number set, that first one, and we'll take a little trip through time. So when you were in kindergarten, you started and you learned how to count. And the first number you learned to count was probably from about 1 to 10, because that was how many fingers you have. And so you learn to count 1, 2, 3, 4, and those numbers actually represent the natural number system. And so we generally call those the naturals, or we'll call them the counting numbers, or counting numbers. And then once you get out of kindergarten, you learn how to count to, say, 100. You realize that there's a lot more numbers out there, and you learn about this new number, and it's called 0. And we consider the natural numbers plus 0 to be another set of numbers that's a little bit bigger, and those are called the whole numbers. And so that's actually going to be denoted by this brown or this brass ring right here. That this is all of the natural numbers plus 0, and that's it. That's what makes this new number set. And then once you got into about middle school, you started learning, well, okay, there's not only positive numbers, there's a whole other side of the number line that we have to deal with, and those are going to be the negative numbers. And we take the whole numbers, or the right side of the number line, we join it with the left side of the number line, and we actually get a number set called the integers. And you probably heard this word before, integers. And it's just every single number that is between negative infinity and positive infinity, and there are no decimals to it. So those are just solid numbers. You wouldn't say they're whole numbers, because whole numbers are their own set. And then once you got into high school, you started, well, there's numbers out there that are not nice, and they're not integers. And we can say, well, there's these two numbers. There's decimals, and then there's really ugly decimals. And so those get broken down into two sets. And so the first one is the irrational number set. And you probably learned about this one second, but the irrational number set has to deal with, well, if I take the square root of 3, I get this really gross decimal. Or I also learned that the first irrational number that you probably ever learned about was pi, where it's 3.1415, and it keeps going on forever. Irrational numbers are non-repeating, non-terminating decimals. They're sometimes represented by Greek letters like pi, or some other letters like E, which is a letter we'll deal with, or a number we'll deal with later in the year. And if you notice in the diagram, they're actually their own subset. They're not part of any of these other subsets. And then the other numbers that you started to learn about, say, when you got to later in middle school, were the decimals and the fractions. And these are called rational numbers. And a good way to remember that they're rational numbers is that the word ratio is in rational numbers, meaning that you can take any number that is a rational number and you can express it as a fraction. Even repeating decimals can be expressed as fractions. And so that makes up all of the number sets that we're going to deal with. Now, to simplify convention in writing, we don't actually have to write natural numbers, whole numbers, integers, irrationals, rational numbers, or even real numbers. We have letters that are assigned to each number set to make things easier for us. So, for example, the natural number set is going to be n, and this is how we write it. There's special ways that we write them. W will be a W. Z for the integers is going to be Z. It's my favorite one, actually. I will have 2 bars in it. Q will have 2 bars in it. And then finally, the real numbers will also have 2 bars in it. And each one of these letters are specifically tied to these number sets. So if you ever do write any one of these, I know specifically which number set you're talking about. And you're not talking about anything else other than a number set. Now, the reason why we have these is because sometimes sets are too large to express easily in set notation. To account for this, set theorists developed something called set builder notation to describe elements of the set. In set builder notation, you describe the properties of all the numbers of that set and describe those properties instead of listing out every element. So for example, a list of A is the set of integers between -3 and 16. Now, if I really wanted to sit here, I could write out A as the set of integers between -3 and 16. So that's between -3 and 16, and I don't even know if I'm including it. Let's suppose that I am including it. So I would say, okay, it starts at 3, and then it goes to -2, -1, 0, 1, 2, and it goes all the way to 16. Now, that would be a set that has 19 elements in it, and I don't want to list out all 19 elements. So what set theorists have done is that they've created something called set builder notation. It looks like this. These two sets are saying the exact same thing. They're saying the same thing. Now, the way that set builder notation works is that you're going to use your curly braces still. You're going to declare a variable, and so let me clear some of this out so that you can actually take some notes on it. So the steps to writing in set builder notation are as follows. It's clear. Come on, there we go. Is as follows. The first thing that we're going to do is we're going to declare a variable. And so I'll say I have the set A, and it contains X, and then we put a little bar in between the X and the rest of the set, and this little bar actually means such that. Okay, and now all I have to do is list all of the elements or state a relationship between all the elements in the set. So I'm saying that it's all the integers between -3 and 16. Well, I can express that as an inequality or a compound inequality. So I can say, okay, well, this is the set A that contains X such that -3 is less than or equal to X, which is less than or equal to 16. So this is going to be my relationship. Or property. Now, it won't always be an inequality. Sometimes you're going to exclude values. Sometimes you're just going to be using an algebraic expression. But this property should handle everything that's in the set. So this is the set A that contains X such that -3 is less than or equal to X, which is less than or equal to 16. And then the last thing that you have to do, so the second thing you did was a property or a relationship. The last thing that you have to do in set builder notation is you have to assign X, or assign your variable, to a number set. So for example, if I'm saying X is all of the integers, I'm going to say, well, it's X such that -3 is less than or equal to X, which is less than or equal to 16. And I'm going to say X is an element of the integer set. And that's going to handle this relationship, and it's going to be much easier to write than writing set A that has 19 elements in it. So let's try an example with it. Describe the set of numbers using set builder notation. So if you look, I have 8, 9, 10, 11, and this ellipsis, which means that it goes on forever. So there's a couple things that I need to do. One, I need to declare a variable. I'm also going to call this set A. So this is A. And I'm going to say, okay, this set is going to contain X such that it looks like all the numbers that are greater than 8. And it also looks like they're either whole numbers or integers. Why don't I say that they're integers? For the most part, if you're ever going to see numbers that are whole numbers, either positive or negative, you can assume that they're in the integers and you'll cover your bases. So I'm going to say, Well, it's all the numbers that are greater than 8, including the 8. So I can say, well, x is greater than or equal to 8. And then the last thing I have to do is I just have to assign x to a number set. And I said, well, okay, since it's whole numbers and I can assume that they're positive, why don't I just use the integer set to be safe? So I'll say, okay, x is an element of the integer set. Similarly, I could also say that x is an element of the whole numbers, and I would be correct. Or if I really wanted to go so far, I could also simplify it way down and say x is an element of the natural numbers, because these are all considered, or these numbers are all in each one of these sets. Let's try this one. So let's say every real number less than 7. And we'll include the 7, or we won't include the 7. So we're not saying less than or equal to, we're saying less than 7. So for this, I'll make my set A again. And I know that's going to contain the set x such that, well, it's all the real numbers less than 7, so x is less than 7. And then the last thing I have to do is I have to assign x to a number set. Well, I'm saying it's every real number, so x is an element of the real number system. Now that means that I can pick any number, decimals including, all the way up to 6.999999999, and it'll be an element of this set. This is a very large set. You would not be able to list every single element of this set. This would be an infinite set. It's impossible. The last one is a really weird one, and it just deals specifically with properties. So let me get this out of the way. So if I want to think, well, I want all of the multiples of 3. So if I start listing out all of the multiples of 3, so that would be 3, 6, 9, 12, 15, 18, and this would go on forever, right? But the way that I can think about it, well, I know that this is really just 3 times 1. And this is 3 times 2. And this is 3 times 3. And so generally what's going to happen if this is 3 times 4, 3 times 5, 3 times 6, what I'm taking is I'm taking 3 and I'm multiplying it times some number that's increasing by 1 every single time. And it's also increasing by an integer every single time. So I can say, okay, well, I'll make set A, and I'll declare a variable again, and I'll call it x, such that it's going to be 3 times whatever that number is. And as long as I set it in the integers, this will generate every single number in this set. A second type of notation that we have is something called interval notation. So this notation uses inequalities to describe subsets of real numbers. The symbols, or I will either use square brackets, are used to indicate endpoints that are included in the interval, and parentheses are used to indicate endpoints that are not in the interval. The symbol infinity, positive infinity and negative infinity, are used to describe unboundedness of an interval. That means that it has no end. So, for example, all of these sets that go on forever, we would say that this one goes on forever until infinity. And this one would go on forever until infinity. Okay, so let's put this table in our notes. Probably going to want to pause the video and put this in. Okay, let's take a look. Okay, so if I want to say, well, if I have a bounded interval, which means it has endpoints, and so if I have 2 endpoints A and B, and I want to say A is less than or equal to X, which is less than or equal to B, the interval for this notation, or for this inequality, would be A brackets A comma B. Or if I wanted to have an unbounded interval, or I would have a bounded interval, where it's still A and B, but now this time A and B are not included since it's not less than or equal to. Those would be with parentheses. And you can also mix and match. So if in this inequality A is included but B is not, well, I can say, okay, well, I have brackets on A and parentheses on B. And similarly, if it's on the other end of it, well, then I can say parentheses on A and brackets on B. And those are bounded intervals. So that means that you're always going to have two specific endpoints, but you might not include both endpoints. If we start shifting to unbounded intervals, it means that one of these symbols on the inside of the interval is always going to be infinity or negative infinity. So you have to start thinking, well, if x is greater than or equal to a, then a is going to be the smallest possible number that I can have, and so the interval is going to go from a to positive infinity. And if you think about, well, if x is less than or equal to a, that means that a is going to be the largest possible number that I can have. And so it's going to go from negative infinity to a. One thing that you should always note is that you can never put a square bracket on infinity. That would mean that you're including infinity, and that actually doesn't make sense mathematically. Now, if I say that x is just greater than a, that means that a is not included, and so it would look like that. And if I say, okay, well, x is less than a, which means a is the largest number, but I'm not including it, it would look like that. And finally, if I see that I have a compound inequality that says negative infinity, which is less than x, which is less than infinity, that means that you're spanning the entire number line. And so you could actually just say negative infinity to positive infinity. We're going to be dealing with this one a lot in terms of domains of polynomial functions. The domain of a polynomial function will generally be negative infinity to positive infinity. Okay. So let's try writing some in interval notation. Write each set of numbers using interval notation. For a, I notice that the 8 is not included, but the 16 is. So that means I'm going to have a parenthesis on the negative 8, and I'm going to include the 16, which means I'll put a bracket around it. This is also a bounded interval. Since this one is unbounded, so its x is less than 11, so this is unbounded, you ask yourself, well, what will be the largest thing in this interval? Would it be the 11 or would it be the x? So since x is less than 11, this interval is going to go from negative infinity, since 11 is going to be the largest possible thing that it could be, to 11. And since it's not included, this will also be in parentheses. Okay. The last one is weird, and we generally don't use this too much, but you should notice it just in case you come across it. So if I say x is less than or equal to negative 16, or it's greater than 5. So basically what I'm going to do is I'm going to treat each one as its own unbounded interval. So I know that x is less than or equal to negative 16 is very similar to this one. So I know that it's going to be negative infinity to 16. And since the 16 is included, I'm going to include the 16. And I'm also going to write this one, so x is greater than 5. And I know that the 5 is not included, so I know that it's going to be 5, and it's going to go to infinity. Now the way that we join these together, because we have this or in here, is that we use something from the set work that we did yesterday. So we're going to use a union symbol like we did for the union of two sets. What this will do is this will join two intervals together and basically exclude the middle.